Welcome all to our GNR638 project, Arcface, a state-of-the-art face recognition model. Now I'll take you through the initial stages of the project. We wanted to build a face recognition model which could do both face verification and face recognition. So we looked at all the existing techniques and the papers which are related to them, the SOTA models or the state-of-the-art models for them, and that's how we discovered about Arcface. Now on to the existing methods. Some of the existing techniques were the triplet loss. The triplet loss finds the reduces the difference or the distance between positive true pairs and different or negative pairs. It tries to put a margin between those. The interloss tries to separate or make the distance between two classes much different from further apart. The intraloss tries to incorporate intra-class compactness, or the embeddings of people. They are more compact together in hyperdimensional space. The margin loss, Arcface is an example of a margin loss where the distance from the embedding or the photo to the weight of that class, or the weight can be thought of the center of the hypersphere in which the whole class exists in hyperdimensional space. So the distance between the pair, the photo and its classes weight and the other classes weights are it is lesser than the distance from the other classes weight. This makes sure that there's a margin, or discriminative features can be learned in this model. So the most of the existing methods, we started to search for papers where these methods are used and the best of these methods, which were the best. So we looked at some of the generative one-shot things, but these were GAN, and which would make the project much more complex since we have to learn a lot about GAN implementations, etc. The other papers which we went through, some were quite basic, but they were not state-of-the-art and were quite old. This FaceNet over here uses triplet loss and was the SOTA, but I got replaced by Arcface, SphereFace, CosFace, and so on. SphereFace is one of the margin loss things which papers which came before the Arcface loss, and it was the state of the art before it. We chose Arcface because of its simplicity, its robustness in training, and it did work out quite well. We read this paper on deep face recognition, a survey paper on various deep face recognition models, and this connectedpapers.com also helped us in a search for papers to find out Arcface. So the Arcface paper is pretty concise in terms of the concepts. It explains all the concepts quite precisely, the geometric meanings, the loss function, etc., and it talks a lot about the performance studies of the Arcface. The performance studies were not as important for us, but the description of the Arcface loss function was quite important, and I'll be giving a brief overview of this project, which is the Arcface loss function. So over here we can see that the embedding is gotten from a pre-existing backbone such as a ResNet 50, ResNet 34, or whatever. In our project have used a ResNet 50 for using pre-trained ImageNet weights in order to get the embeddings of the weight. This is the Arcface weights, the Arcface weights which are present in the Arcface layer, and these Wi can be imagined as the center of the classes of the particular class, ith class, you could say. These two are normalized, the embedding and the weight are normalized, and they are multiplied to get the cos of theta. So the theta j is the the angle between the jth class, the weight of the jth class and the embedding, and we take the arc cosine of it in order to get the angle theta between them, and we add a angular margin to it. Now we don't multiply it with the weight of the same class. So if xi is that, we don't multiply it with the wi, we multiply it with wj, where a is not equivalent to I, and we get the angle between that embedding and the weight of the different other classes. We add a margin to this because we need interclass separation. So we add a margin to this angle, we take cosine again, scale the feature back. So I mean, once you take the cosine, the weights over here can be thought of on as staying on a hyperdimensional sphere of radius 1. We scale it in order to get a hyperdimensional sphere of radius s, and then we do softmax in order to get the class of it. Then we do the regular kind of cross entropy loss in order to update all the weights, and that's how the Arcface loss works. So here is the mathematical description of the Arcface loss given over here, and between Arcface and previous sort of models such as softmax. Over here you can see that this is an example of 8 different classes of people which were trained on the Arcface and the representations in 2D space. You can kind of think of it as a PCA, but and the softmax does separate them, but there is the boundary region is not quite decisive. But in the Arcface, since there is an angular margin which is added between the classes, there is a clear distinction between where the classes lie in hyperdimensional space. Over here we can see the difference between sphere face, cos face and arc face, and a geometrical interpretation of those in terms of binary classification can be given. Decision boundaries are drawn over here. Arc face gives a clear separation between these two. Sphere face and cos face also does a good job, but the separation is a non-linear function. But in the case of arc face, the separation is quite well defined, and it is linear in nature or constant. Over here, the origin losses of sphere face, cos face and arc face have been kind of like put together in terms of hyperparameters. So the M1 over here is used in sphere face, and it is known as the multiplicative angular margin. You can kind of see that the equation over here can be translated into the decision boundaries. So M1 is the multiplicative margin, M2 is the additive margin, that is in the case of arc face, and in the case of cos face, M3 is used, which is the additive cosine margin. So yeah, and you can see that the cosine is a non-linear function, so you can kind of see a non-linear decision boundary in cosine face being reflected over here. We used TensorFlow framework, design, build, as well as train all the models. We used a pre-processed LFW datasets, a partial set of it. So we used the OpenCV backend detector to detect the faces and process them and store them as images, converted them into 112 cross 112 cross 3 vectors to be put inside our ResNet backbone framework and get an embedding from it for our Arcface thing. We stored it as X, which is our data set, and in the first thing we used the methods suggested in the paper. As per the pseudocode of the paper, we designed the net Arcface layer. We had to make a customized training code for a training loop for the whole training, because in the training itself we use both the labels as well as the training data or the photos. So instead of the normal way where we just put in X and finally only while finding out the loss, we try to we compare it with the labels and do cross entropy loss or whatever loss which we are looking for. So we had some problems with saving formats, in the sense like initially we did save weights, which gave us a lot of problems since it was kind of like it was a customized model, and we had to shift to the inbuilt TensorFlow models and not as .h5 file function in order to find the angle between the center of the weight center as well as the embeddings, was that it wasn't very stable in training. After about 800 or 820 epochs, it always started to give problems in the training loop. We use the Atom optimizer initially. So over here you can see that this is the Arcface layer, the training loop which we have defined. We use the Atom initially, so this is the training code version 1. When we used to take the Arcface weights and we used to see them, there would be all NaN values in this position. So we had to look for other ways in order to solve this issue, and thus we looked at other third-party implementations and we came to our second model. The optimizer which we saw in the other third-party implementations, as well as the inside phase, which is the actual implementation in MXNet, not in TensorFlow, by the authors of the Arcface paper, had SDD optimizer, which we further used for further applications. Then we also use the cosine method instead of the arc cosine method. So what exactly is this cosine arc cosine stuff? So okay, over here you can see that I've used the ACOS method to find theta in this case, the initial. This was what was suggested by the paper, and we have implemented it directly according to it in the initial one. But this did not work properly. It gave that non error, which I have just talked about. So instead, the third party implementation, what they did was essentially what you need to do is find theta, add a angular margin to it, and then take cos of it again. Instead, they just use the cos formula, cos A plus B is equal to cos A cos B minus sin A sin B. So they did that kind of method, and this proved to be much stable while training, because as you can see over here, this was when we used the cos method, we could train it till about 2300 epochs. We thought our data set was too small, so it could lead to overfitting, and searching for a new dataset, all the datasets were super big, and this was the smallest dataset which you can find, which was still 0.5 million or 5 lakh images in size, called the Cassia Webface database dataset. We use the cosine methods, but still, and the STD optimizer. Still, it gave us some problems, and the training was so long that it couldn't even reach to 1 epoch before we had to stop training. And we do the training on a collab, so it wasn't that fast also. So you can just see the loss function thing is over here. We couldn't save any weights properly. This is the Cassia Webface dataset, which we have converted into a TF record after downloading it, and it is still 2.5 GB large for the 0.5 million images it consists of. It's primarily used for face recognition and verification. We also need to calculate the threshold for determining whether the two photos given or two embeddings which are being compared are the same people or from different people. So in that case, we need to write functions for all these. We have written functions for all these by recognize, verify, etc. And I'll just give you a short small kind of demo for the same. So we have taken in the model from function gets the distance, particularly the cosine distance between two embeddings which are given to it. The face verify is a function where you give the image paths to two images. It gives whether the images are of the same people or different people. For instance, over here, first I've given two images of Angelina Jolie. It shows that the cosine distance is 0.07, and it is of the same people, so it is correct. Here, one of Angelina Jolie and Arnold Schwarzenegger, and it gives a distance of 0.10 something as the cosine distance, and it is of different people. I've given the threshold to be as 0.075, and thus it gives the same people and different people accordingly. It does not mean that, which implies that we cannot, the model does go wrong. Over here, there were two images of Arnold Schwarzenegger are given, but still it classifies them as different people. So yeah, calculating thresholds is quite a big task, but you do remember the distance plots which you have seen in the previous visualizations, and this came from this calculate threshold thing, where I take calculate pairings of same people and different people, calculate the threshold calculate the distance metric from them, and from that calculate the threshold. We kind of wanted to stop the project after we had finished the model, and it worked quite well in face verification and recognition, but we wanted to try out deployment, and so we did. We used Flask, a little bit of JavaScript, and Ajax for the server front and backend communication, and built a simple interface using HTML in order to do the same. So yeah, here's a demo of the same. Actually, I've started the server over here, or the Flask application in this case. This is the face recognition site project. This is the app.py, which contains most of the important information and most of the code in it. Yeah, and the models are stored inside that. The Arcface model is stored inside that. Right now, so I'm in this socket right now, and yeah, first I'm choosing phase 1. Yeah. And I upload it. So once I upload it, I can go and see that it has been uploaded as phase 1 over here. Yeah, so right here. Right. So the second phase is the phase which I uploaded, the previous attempt, or after after I upload the second phase, I can come and see over here that it's indeed the second phase. Yeah, you can see the name over here. So it comes in the uploads, and then when I click verify, it passes it through the embeddings I got, and then it is verified. Right now it is the same people. So yeah, okay. And we could also try another different set of faces. So we could try this, and we could try this guy. Even if it is a image of different dimensions, say not 112 cross 112, it resizes it in the pre-processing before it actually processes it and gives out the result. They are different people, and it gives a different people as output. So it works pretty well as expected. So yep. And the templates have the base and the indexes this whole thing. Just to make it cool, we added also this toggle thing. That's it for now. Thank you for viewing our project. We hope you like it.